Okay, so we're going to look now at Introduction to Differentiation. So this is not using first principles. This is just what we're going to call differentiation by rule. Okay, so we're going to look at the rules that go about differentiating polynomial expressions, the chain rule, product rule, and quotient rule. Okay, so differentiating polynomials, section 1. Okay, background info. Okay, differentiating or finding the derivative means finding the instantaneous rate of change, that is the gradient of the tangent of a function y equals f of x. It's important to know thoroughly the notations associated with this operation. Okay, so the original function is called y or f of x, then the derived or the derivative is called dy by dx or f dash of x. Okay, we sort of know that. Okay, so we want to get learn how to easily differentiate polynomial functions. So if we have a look, what this gives some examples of polynomials. Okay, 3x to the fourth is a polynomial. It's a polynomial of order 4. 5t take 7 is a polynomial in t of order 1. 5, this one here, 5 on x times x to the minus 3, or 5 on x cubed plus a half x. These are all polynomial functions. Okay, and they're really quite easy to differentiate. This is a polynomial on x to the, it's an order 0. It's just a constant. Okay, now, these bottom ones, these are not polynomials. Ooh, this one would be if you expanded it out. This one isn't. That's an exponential. That's not, and neither is that. Okay. So that one, that's a bit of a silly one to put in there, because if you expanded that out, that is a polynomial. But, yeah, okay, we'll go with that. Study the differences closely. Okay, well, all right. Okay, differentiating polynomials. This is functions that look like a, where a is a constant, x is your variable, and to the power n, where n is just some integer number. So n could be 1, 2, 3, it could be a linear function. If the n is 2, it's a quadratic. If n is 3, it's a cubic. 4 is a quartic, okay? This is the most basic form of differentiation. The rules you must learn are as follows. Okay, if your function is just a times x to the power n, then the derivative of that, and that's how you denote the operator, the differential operator. Okay, so what we're saying is that the derivative of this polynomial function ax to the power n is equal to nax to the n minus 1. Okay, are they going to give us an example? No, they're not just yet. Here's the second rule. If it's just a times x, then the derivative is just a. If you actually just put n equals 1 here, you can see that that's just a special case of this one. And the last one, the derivative of any constant is 0. Because you imagine if you had a constant function, its slope is 0. Okay, I think they're going to do a few examples of this. Okay, examples to try. D by dx of 3x to the 5th. Let's see what they do. It's 15x to the 4th. So, okay, what they did, note the 3 and the 5 are multiplied. Okay, so you take the 3 out the front. Just forget him for a minute. And then this one, 5x to the 4th, n is 5, so 5 came out the front, and then we just took 1 from the power. So we got 3 times 5 times to the power 5 take 1, which was 4. That followed our previous thing, that the derivative is nx to the n minus 1. So this one here, we've got two different terms that we want to differentiate. So this is like a function, f of x equals x squared minus 5x. This is a quadratic. And if we just apply that, the x squared is treated as one lot of x squared, so it just becomes 2x. And the 5x just becomes 5. Okay, if we apply the rule that x to the n, if we've got a function f of x equals x to the n, then the derivative of that is nx to the n minus 1. Here x is 2. So it's like we take the 2 out the front and then we subtract 1 from here. That gives us our 2x. This is 5x to the 1. If we take the 1 out the front and 1 take 1 is 0, x to the 0 is 1, and there we go. Next one, here's another quadratic. So I predict this is going to be 4x take 3. Remember, the derivative of a constant is 0, so it just gets wiped out. So let's have a look. 4x take 3. Okay. Okay, the alternative phrasing this, okay, y dash merely means, okay, that's okay, we got that easy. Oh, so we've got the last one here. Find y dash. Pardon me. So here we go. We're going to use this rule. It's 3, y dash equals 3 times, now what we do is we take the 2 down the front. So it's 3 times 2 is 6. X to the 2 take 1. 2 take 1 is 1. So that's going to be a 6x. Now it's minus a half. We just leave that half there. Take the 4 down the front. And this is going to be x cubed. And this is take 1. Okay. So let's have a look. There we go. 6x squared. Take 2x cubed. Take 1. Have a go at those yourselves and make sure you don't move on until you understand how you got those. Okay. It's all based on the rule, the previous rule that we did. That was right back here. There, d by dx of a x to the n equals n times a times x to the n take 1. Okay, it's all based on those three rules. Write them down so you can know where to go afterwards. Okay, we'll just go back now, go through all of that and go to the next slide. Disguised polynomials. What the heck is a disguised polynomial? Got no idea. Okay, many expressions don't look like polynomials at first, but you can turn them into polynomials by removing brackets or cancelling fractions, as in the following examples. Okay, let's just have a look what they're talking about here. Okay, yeah, this is like, it doesn't look like a polynomial, but if you expand this, you do the FOIL, you end up getting there. Nice little quadratic, which is now polynomial format, so it's differentiable. It's easy to do with the rules that you know. Okay, so f dash of x is just 18x minus 30, using our rules from before. Okay, just going to go on a little bit further with this one. Oh, if the power were higher than a square, oh, don't worry about that. The chain rule, we're going to do that later. Okay, expressions we can put into polynomial format like that. What are they talking about here? Oh, okay, if y equals that, find dy by dx. Well, we're going to do a FOIL here. That's the difference of two squares. That's going to be x squared minus 49. Okay, we know this one. Y equals x squared 49. We're now in polynomial format. It's easy to differentiate. It's going to be 2x take, and the derivative of a constant is 0. So this is just going to be 2x from out using our rules before. Okay. Okay, with just this last little bit here, when multiplying a whole number, what are they on about here? Yeah, this is just to manipulate these expressions will be very handy. Okay. Example, what are they talking about? Differentiate this one. Okay, so you've just got these numbers. You've still basically, this 3/5 is just like your A. Okay, so it's going to be 3/5 times 8. This is the derivative of this thing, times x to the 8 take 1. Okay, and that's just going to give us, okay, they're going to rewrite it like that. It's virtually identical, isn't it? Just like that one. And it's just going to give you that. The 24 came from the 8 times 3, x to the 7th, and the 5 just stays there. Okay, that's all we'll do on that one. The main thing to remember was this one back here. We'll just go back to it quickly. We can find it. Not all that stuff. Disguised polynomials. It was all going back to this thing here. If you've got a function that's ax to the n, then the derivative is n times a. And of course it could be a times n. It doesn't matter which order you put these in, because they're all being multiplied together. N times a times x to the n to the minus 1. So whenever you get a function, work out what a is, what n is, and then using this pattern, you can find what its derivative is. Okay, that'll do for now.